So it's time for the next talk. We have Tish talking about energy monitoring. So thank you very much. Let's go.
Yeah, can you hear me? Cool. Yeah. So the theme of the talk is sort of reverse of the way the car talk went. I will talk about software first, then I will talk about the hardware. So I have been like sort of doing energy monitoring for a few years now, not in any scale or commercially, just as a hobby, fun thing. So this is sort of the story behind it. I started doing it some 4 or 5 years ago. The SA electricity prices were very high, and my wife, who is very consumption conscious, was randomly turning stuff off, turning off the server where the movies were, or the media center, or anything else that's on. And then around the same time, my son was born, so I was not sleeping very much at night, so I decided to pick up a new skill. So yeah, and I built my own energy monitor. I looked around in the market. There were some things like FRG. Sonoff was not a thing back then yet, 5 years ago, where I wasn't aware of it. There was Open Energy Monitor, which was Arduino based, but didn't have like Wi-Fi. You had to have like a host Raspberry Pi, so it was a large complex system because the host didn't have Wi-Fi on it back then. And I wanted to gather my data. This was one of the initial versions I built. So it uses an ODMCU, ESP8266, an ADS1155, which is like a ADC, because in order to measure energy, you need to measure voltage and current. And the ESP8266 has one ADC, so you need to do some sort of hackiness to get it to 2. You could use a multiplexer. You could add another ADC on top of it, analog to digital converter on top of it to sample both of those analog values. I decided to use a really bad choice, which it turned out in retrospect, slow analog to digital converter. Using family connections, my brother-in-law is an electrician, so he installed this in my DIN rail for me. There's a 12-volt DIN rail transformer, and then a current clamp behind, which is sampling the current, and then it goes off to this thing on the side, which has Wi-Fi, has the ADCs. I have the newer version of the same here. I have 3 of them, which use a different technique. So let's go to what it requires to monitor your energy for sort of an electronics level. You need something to power the thing, a battery, a transformer, a switch-mode power supply. Like, for example, the FRG only uses batteries and then a current clamp onto your power current line. So it's really simple to install because no 240 volts is involved. But the whole thing is that it assumes that you always have 240 volts, so you may or may not get the right readings. You'll get an indication. And then you cannot measure things like power factor, which is the lag between the voltage and the current. You have to sample the voltage. You can assume that it's a set value, which is one way to do it. You can use transformers to take the 240 volts, sample it down. You can build resistor ladders. So you have your AC 240 volts, you have some very big resistors and a small resistor that you tap off, and then you sample the voltage into an analog to digital converter. You have to sample the current, which you can do using current transformers, CTs, I have called them here. Shunt resistors, which are like just lumps of copper with very precisely calibrated resistance. Rogowski coils, I'm not sure, I've never heard it pronounced because I'm not a practicing electrical engineer, only a trained one. And then some people have also these clamp meters which use MEMS, so they can measure like both AC and DC. You just clamp it on, and then based on the current, there's a magnetic deflection, and you can measure AC and DC currents. You have to multiply these things together, the voltage and the current samples, and produce energy. So there are advanced ones which use like CPLDs, FPGAs. You can do it in software when you multiply on the sample your ADC, have a couple of numbers in your Arduino or whatever software you have, multiply by 10 together. You can also use a dedicated IC for this purpose, where the DSP and the sampler and everything is baked into it, and you just read the energy or the power out of it. So these sort of ICs are what are actually used in smart meters. So there is a whole subset of ICs from most of the big vendors, Silicon Logics, Analog Devices, not from Texas Instruments, from Atmel, now Microchip, which do these things. You have to manage the system, to collect all the data, send the data out, some sort of RF thing if you want to do it wirelessly. There are all these variants of RF now, LoRa, Wi-Fi, Zigbee. So this is sort of the latest build. I have gone through lots of different iterations of mixing these things together and trying to cook up a meter that works. So the current one uses SMPS 240 volt to 5 volt resistor ladder, and then CTs for current sampling, an ASIC from Microchip Atmel for performing the energy computation, which sits on a serial peripheral interface, SPI Bus, ESP32, and then this talk is about sort of transitioning, like the previous talk, about transitioning from the ESP32 to something else, like a Linux compatible thing with more resources or more ease of development once it has been like baked into your thing by an electrician and you don't want to touch it again, right? So it's good to have SSH onto it. You are not going to have USB again, possibly. So you can SSH onto it and then run some Python scripts to mess around because you're a software person and you don't want to go and touch the hardware again. It's been baked in place. I'm sure that it's possible in ESP32 to update it in some fashion, but you may feel too much of a risk breaking it and then going through the whole call an electrician loop to fix it. And then sort of pushing the data over MQTT to some Mosquito or one of the AWS, IBM, one of the cloud-hosted IoT platforms. So I'll pass this around, or you can come see me. I'll pass this around. I'll do a demo. I'll pass this around. I'll pass the whole bag around. Yeah. So just I was saying asides about doing stuff at home. So I have a very supporting family. I did a small crowdfunding run for these kits. And here is my wife trying to crimp some cables, or she did a very good job, not trying, but did a lot of the interface cables, which does the off-the-shelf CTs you can get, and then makes an adapter that goes into the energy monitor. So here's the section about the SPI bus. How many people love or hate or know about the SPI bus? Yeah, 50 or more, okay. So yeah, the SPI bus is quite common in microcontrollers. Some others try to fake one using BitBang. We'll talk about that in a minute. So now the SPI standard has never been standardized. So there are more and more lines being added. There is the SD cards, micro SD cards use something called a quad SPI with 4 data lines. Most IoT grade ICs or even the SPs have SPI flash sitting on it, on the hardware SPI. There is a flash to give the storage for the code and such. And then here is like an aside on how weird the SPI standard is. There is some FPGAs coming out with HexaSPI, 16 data lines on the SPI bus. Yeah, why not? It's really serial if you have 16 lines. Yeah, so the SPI has lots of modes. It can be, like, depending on whichever way it's implemented, based on the phase between the clock and the clock and the data lines. And so you always have to check your sheets to see if you are using the right mode. the data sheets, and then sometimes if the chip select is deselected, which says I'm using this, because you might have multiple things. If you deselect it, some devices will like go to sleep, and then it has to recycle again. So which we'll talk about in half duplex SPI modes that I have to use. And then this is sort of the history of the SPI support in the Linux kernel, because I'm sort of moving up to something that supports Linux in a particular MediaTek CPU. So the MediaTek CPUs are down here, the MT ones. They're actively in development. There have been commits for their SPI drivers 4 months ago. The SPI drivers for them are still being stabilized. The initial bitbank GPIO SPI was written in some 10 years ago by David Brownell, and then there has been the hardware drivers keep on being updated as new SoCs come online. And then you have to patch the I/O controls to user space. So for ease of development, I've chosen to use OpenWRT with CPython. So you have to patch the I/O controls from the SPI up to this particular variant of SPI, MediaTek SPI, is half duplex, and you have to write some weird function to keep the chip select on between send and then open a buffer and then capture the stuff that comes back after you have said, I will read this register, write, then keep sending blanks, and then the kernel will give you back 2 more bytes that you have read. And it's just the xfer3 is just there to keep the clock going. So and the chip select has to be held active, otherwise the chip will think it's a new transaction and lose your request. Then the initial stuff I wrote in Arduino, just as a retrospect. And this also had trouble because the SPI was implemented in a flipped fashion in the SPI266, which was my initial host controller. It stayed flipped for a couple of years. So actually, now it has been fixed, and I'm receiving issues or pull requests to say, how can I have the same code running in an old IDE and a new one where it was broken and now it's fixed. So just check the version of the SPI if you're running with stuff. Anyway, so because of the lack of standardization of SPI and the mismatch between different implementations, it can be quite difficult. Even though you're not doing maths and multiplying, if you have written an SPI driver for a particular chip which does it all, then you still have a bit of workload left to make it talk to the host processor. So I often do development interactively these days on the ESP32 with Micropython. It's really good. This is just a demo of like a demo I will do later to show how to do the energy readings in a notebook, connecting to the Micropython kernel, connecting the Jupyter Micropython kernel over the serial port to the host ESP32, and then trying stuff out to make sure I got the SPI mode right. And I also wrote I was going to do this demo as well, which is the OpenWRT board, so which you can see off here. OpenWRT board, which I'm running. This particular board I chose as opposed to a Raspberry Pi or something with a bigger communities because it fits in the DIN rail, which I will talk about in the next slide. The Raspberry Pi is a bit too big to fit in the 2 units of DIN rail. This is just the right size. Anyway, so it has register list. It has the hacky, or not hacky, now working SPI communication protocol, basic initialization, and you can read stuff off it. And then the next step, which makes having a Linux host makes it easy, is you can do MQTT, have certificates, encrypt your stuff if you're going out to the public cloud, and then just register a device and then send what Amazon calls device shadow, which is the current state of your readings up. So you can use PAHO and nice Python libraries to do that. So this is the plan. So read the device that is measuring your energy, have a small OLED to show what it is locally for debugging. OLEDs are really useful for debugging. Push it to a remote sync over MQTT TLS. And then also, because MQTT lets you subscribe to stuff because you can also drive relays and such out of the energy monitor to say, I'm going to turn off my aircon, I'm going to direct energy to EV or a battery or a water heater to store or something. So also software side, building the OpenWRT for this particular Onion Omega is the MediaTek-based host processor I'm using. It's quite hard. These days we say, oh, just run it in Docker, it will work, but it's not the case. Previously it works in my machine. Now it works in my container. If you set it up properly and give it enough resources, it will work. So I ended up just focusing on the Python, the C Python module that supports SPI. Can we do similar development in Micropython and Arduino? Arduino ecosystem is very mature. You obviously can, but you usually are linked to like one certificate, and changing certificates is hard. If your device, something happens to it, and someone may read your certificate off and so on. Anyway, so yeah, I think it would be possible if you want to do MicroPython. I will have to go back and see the MicroPython machine library, which supports SPI and N2C and all those things. That will have the same work that I have done with CPython to support SPI redone. Hardware, so in the other order. So this is what I was planning to build. I'm passing the bits around. It may not always make sense how they fit together. This is what I was planning to build with the power layer at the bottom. Sort of inspired by these things in the market. One of them is Australian design, and then the other one is a Chinese one I got off AliExpress and pulled apart to see how things were. So sort of something that fits in a DIN rail, occupies 2 units of DIN rail. And this one has 3G, and the other one is just shows readings on the screen, doesn't have any network. This is a very, very advanced energy monitor design from an American company called Sense. You can see the link below to the teardown I did for it. It uses a host CPU, which is a Satara CPU TI. Uses a CPLD to do its maths, and then has 2 megasamples sampling of the energy of the analog channels. Very, very fast sampling. And can apparently do machine learning of the energy signatures and such. So this is the target enclosure where all this hardware will fit. It's off-the-shelf Bud Industries DMB4770, and it has got like a prototype board you can get for the base, which is where I sort of started seeing if things fit together. This is the power layer PCB that samples the voltages, provides power. It's again going around. This is the measurement module, which has 3 ASICs from Microchip. So it's modular. So if you decided to try a different ASIC, you could like swap this out to a different one. A new one comes out, which samples faster. Or you have built something using FPGAs and CPLDs, so you could swap this out and then plug that in and sample faster if that was what you were doing. So it's designed for experimenting. It's not a production system, but it'll fit in the DIN rail. And yeah, so this is how far I have got with the actual hardware with the Onion OpenWRT hosted. So last linux.conf in New Zealand, I had it still on breadboard, and now I have made like a little host that fits on top to replace the ESP32. But again, I'm not all the way there. Live demo, yes, okay. Okay, I'll skip the Onion demo, which is gonna be probably dangerous, and I'm gonna do the other one. Okay, let's do the Onion demo. So I'll start here. So basically, this is an SPI Bus demo. So it's waiting for trigger. So that means it doesn't have any data coming in. So if I boot the onion, we'll start collecting data, and you'll see the boot taking place here. Standard Linux boot, it's loading stuff. And yeah, so this is where you can have a look. Yeah, so you can see the clock runs at around 250 kilohertz. So this is the SPI bus that's reading the external flash ROM from which it boots. So one of the caveats for using this is you cannot have the energy monitor connected to the SPI bus during the host booting, because it uses the same SPI bus to read its ROM. So if you have something else, then you have to explicitly have it on high impedance and then turn on via some GPIO, turn it on and put it on the SPI bus. If you have it plugged in during boot, the host will not boot. So that's sort of what a SPI bus transaction looks like. And yeah, it's just reading stuff, and there's a clock. And so that's good. AWS IoT stuff I have prepared. My preparations worked. I'll just run this again. So say you have got some readings and you want to publish it. You can just write some state reporting like that. And yeah, it will publish to a state like this onto a device. This was a while ago at 4th. Yeah, or that was now. That was me publishing stuff. Okay, that works. And then I will do another demo on the Micropython side. I'll escape out of this. And so this is the board connected to a lamp. And I will plug in some 12-volt transformer to sample the voltage. So this is like the less dangerous way to experiment with this stuff. It's because it's ELV, it's only 12 volts. I have got a test tag on my little lamp test rig. Just like if electricians sign off, they carry it on their insurance, liability insurance. So if you have a friendly electrician who will look at your stuff and sign off, you're lucky. Make friends. So it's connected there, and then I am just rebooting, and then setting up a bunch of registers, setting up an SPI bus, and then, yeah, so that section there just does some checksums and says, oh yes, I can communicate to my energy monitor ASICs, all good. And then I'll start running this like infinite loop where it's gonna just get zeros. So if I plug in some power, hopefully the next reading will have some power on it. We'll have some voltage on it. Yep, so that's the next reading. So there are 2 energy monitors plugged to this. So am I getting any voltage? Demo fail. Let's try the other one. Yeah, some voltage came. Okay, I've plugged it into the other one. Let's see how that goes. So the aim of this was to have at least 2 sampler channels for voltage and current, most to encourage like people using solar energy to have generation and consumption. So yeah, so they have voltage there, 241 volts. It's a bit fudged, but you can calibrate it accurately. Resistors in the voltage divider or transformers are not all the same. So you have to put in some fudge factors to get it right to match reality. And then I can turn on this light. And yeah, we have the power there, 17 watts of power being consumed. with usually you don't have the power factor being here. Did I write the code for it? Get power factor, yes. So sorry, I obviously didn't prepare for this demo well, or I am demonstrating live coding on things.
It's so easy to iterate on your design.
Yes. Oops. I unexpected indent. Because my indents are from copy-pasting stuff and they look weird. So power factors on the LED lamps are typically quite bad. So this one has 60. Yeah. So because they have a switch mode power supply and stuff, power factors on them are quite bad. So I'll switch that off. And yeah, it's gone. So that's the end of my demo and my talk. So any questions, concerns?